All right, AP 120, Chapter 2, Topics, Atoms, and Isotopes. So, Chapter 2 deals with chemistry related to living things. And chemistry, it turns out, deals with the composition of matter and how that composition of matter changes. So, basically, we're looking at the smallest level of organization, the atoms and molecules. Now, matter gets broken down into all kinds of different elements. So the elements are the different flavors of matter. There's apparently 118 of them, although most of them we will not have to worry about for human anatomy. Um, and the main elements that we will need to worry about are summarized in this table. The major ones, oxygen, carbon, hydrogen, nitrogen, calcium, and so on. Some trace elements that show up in our bodies, chromium, fluorine, iron. So these are the main elements that we will be talking about throughout the semester. And it turns out that the smallest structure that is still an element with the chemical properties of that element is known as an atom. Atom's smallest structure that is still the element still possesses the chemical properties of that element. Turns out atoms can be broken down into subatomic particles, but these subatomic particles lack the chemical properties of elements. So, for instance, here we have a model of lithium, the element lithium. And as we can see within the atom, here's one atom of lithium. It has neutrons and protons found within the nucleus. So the neutrons and protons are grouped together. They're rather large. Protons are positively charged. Neutrons have no charge at all. And then floating around, spinning around the outside of the nucleus is where we will find the electrons. Electrons are very small and they are negatively charged. Turns out if you took, say, a human, say, weighing 170 pounds, and you said, okay, that human is the nucleus, then the electrons relatively sized would be the size of a mosquito. So electrons are a heck of a lot smaller than the protons and neutrons. Now, again, looking at the periodic table, we see that we can tell how many protons are in an element by looking at the number that's above the symbol. So, number one proton. Number two protons. And the symbol tells you what element you're talking about. So, H for hydrogen, He for helium. So, one proton, the atomic number for hydrogen is 1. Atomic number for helium is 2, and so on. Another thing to know is when we're talking about atoms, we're usually talking about uncharged atoms. And an uncharged atom, or neutral atom, has the same number of protons as electrons. So lithium has 3 protons, 1, 2, 3, and we'll also have 3 electrons, 1, 2, 3. So the 3 positive charges are canceled by the 3 negative charges. There's another concept called atomic weight. Atomic weight is the number of protons in an atom plus the number of neutrons. So this lithium atom, its atomic weight is 7. 4 neutrons, 3 protons, that equals 7. And so sometimes you'll see 2 numbers written next to the symbol for a element. The top number, the bigger number, is the atomic weight. The lower number, the smaller number, is the atomic number. So lithium, this atom of lithium, his atomic weight is 7. Its atomic number is 3. 3 protons, 7 total subatomic particles in the nucleus. Now, it turns out that most elements, actually, I think all elements, are found in forms referred to as isotopes. An isotope is atoms, Isotopes are atoms of the same element. So in this example, these are all carbon. All of these are carbons, where they have different numbers of neutrons. So Same number of protons, different number of neutrons. So for instance, carbon-12 has 6 protons because it is a carbon, and carbon-12 would therefore have 6 neutrons. So 6 neutrons, 6 protons in its nucleus. Carbon-13 would have 6 protons and 7 neutrons, and carbon-14 would have 6 protons and 8 neutrons. These are all naturally occurring isotopes of carbon. And then down here we have the 3 isotopes of hydrogen. So here is hydrogen, where it has only 1 proton, so its atomic weight is 1 and its atomic number is 1. Then we have deuterium, which is another isotope of hydrogen. It has a proton and a neutron in its nucleus, so its atomic weight is 2, its atomic number is 1. And then tritium is another form of hydrogen where you have 1 proton and 2 neutrons, so its atomic weight is 3, its atomic number is still 1. Again, if it's the same element, it's always going to have the same atomic number. Now, it turns out that some isotopes are unstable, and these unstable isotopes are radioactive. And when they break down, they often give off some form of radiation. There are 3 main types of radiation. The first type is alpha radiation, where alpha particles are released. So for instance, plutonium here will break down into uranium and release a alpha particle. And an alpha particle has 2 protons and 2 neutrons. So that means that the plutonium, when it becomes uranium, loses 2 protons, hence it's a new element, and also loses 4 from its atomic weight because it's losing 2 neutrons and 2 protons. Now, alpha particles are very large, very slow, so alpha particles can be blocked by a simple sheet of paper. Then we have beta radiation that releases beta particles. A beta particle is an electron or negative charge. So here is carbon-14. It is radioactive. It breaks down into nitrogen-14. This is because when its nucleus, the nucleus releases the beta particle, loses that negative charge, that means it is going to gain a proton. It's going to become a little more positively charged, gain another proton, so it becomes a new element, nitrogen-14. And beta particles are obviously smaller because they are the size of electrons, and they can be blocked by a sheet of aluminum. And then the third kind of radiation, gamma radiation, releases gamma particles or quantums. And this is just energy being released from the nucleus. It is not an actual subatomic particle of any kind. So that means that we do not change the overall look of barium in this case, barium-137 will still have the same number of protons and the same number of neutrons. It is just less energetic. And it's worth noting that gamma radiation will not turn someone into the Hulk. No, instead it will just cause mutations to their DNA and eventually kill them. And since this is just energy, gamma radiation requires a thick chunk of lead to block it. Half-life. A half-life is the time required for an isotope to lose half of its radioactivity, for basically half of it to break down. And so that is what a half-life is, and it can vary dramatically from, say, millions of years to milliseconds. So the half-life of different isotopes can be quite dramatically different. Now, in medicine, we actually take advantage of some radioactive isotopes for various important medical procedures. So, for instance, there is a isotope of iodine, iodine-131, which is radioactive, and it is used to treat hyperthyroidism. So if someone's thyroid gland is overactive, is producing way too much thyroid hormones, Then someone will be injected with radioactive iodine. It will end up localizing to the thyroid gland, and the radiation will degenerate, will break down the thyroid gland. Less thyroid tissue present, that means less thyroid hormone will be produced. That is it for these topics of chapter 2.